então, bem-vindos de volta. Então vamos continuar com o professor Arnaud Banos, que vem da Universidade de Paris 1 em França, onde já foi diretor do Instituto de Complexidade e neste momento é diretor do Geographie-Cités Laboratory. E no seguimento do que o professor Tendório nos esteve a falar ainda há pouco, quando falámos sobre autómatos solares e a sua importância na modelação, o professor Arnaud Banos vai nos falar sobre sistemas geográficos adaptativos. Portanto, vamos entrar no campo da simulação multi-agente, portanto, na sua importância para o planeamento e também na análise a diferentes escalas que estes tipos de sistemas nos permitem. Portanto, passava a palavra ao professor Arnaud, que ele poderá seguir com a sua apresentação. Espero que goste.
Okay, thank you very much. I'm very sorry I have to talk in English. Well, I can do it in French, much better. But in Portuguese, no way. I'm sorry for this. Anyway, when Patricia invited me, it was supposed to be a small, intimate conference. And it turned into a trap. So many people, okay. So I will try to do my best. I know some of you. I met some of you quite some years ago when I was the director of the Complex System Institute in Paris. And I'm very happy because it seems that things are moving towards collaboration between your groups here and mine in Paris. So I'm not anymore the director of the Complex System Institute in Paris. Now I'm the head of the CNRS unit, Géographie-Cités. And we already have connections because José Antonio Tenedorio presented the work of Raquel de Deus, who is co-supervised by Denis Pumin, and Denis Pumin belongs to my lab. So, and we already have Eduardo, who is beginning his PhD between here, university, and my lab in Paris 1. So the connections are becoming quite tight, and I'm very happy, because I think that what you're doing here is very, very nice. And I'm sure we can go more things in the future. Okay, so I've been working for a while now on complex systems, on big data also, geovisualization, geocomputation, geosimulation. And my talk this morning will be more towards agent-based modeling, with the idea that can agents make a difference? And of course, my answer is yes. But the idea is not at all to put everything towards agents, okay? Because there are strong limitations, and the idea is more to go in the field of playing all together and having different methodologies, working all together. Okay. So let's begin with a very simple game. So some of you may know it. If you already know the answers, please shut your mouth so that the rest of the room can use the neurons. Okay, so it's a kind of mental game. You can do it for real, social simulation. So let's imagine I ask everyone here in the room to choose randomly two people, A and B, and you keep it in your mind. Okay, this is hidden information. A and B, completely randomly. Then what I'm going to ask you, this is the rule of the game, is to make sure that you are in such a position that there is always B between A and you. Okay? So for example, if my A and B, so Paulo and Jose are my A and B, okay, I will have to move here to make sure that I'm not directly connected to Paulo, okay? Very simple. So my question is, what will happen? Can you guess? If someone enters into the room not knowing the rules of the game, what will he see? Any guess? Okay, so this is what you can expect. If you think about yourself, I have to move, but then Paulo is going to move because he has another A and B, and then, okay, I will have to follow, Jose is going to move, so everyone is going to move. Okay, very nice. Then, if we try to describe, to anticipate and describe the kind of spatial pattern we are going to produce, someone is entering into the room, looking at us, what will he see? the game is very simple, okay? You can imagine. But still, it is not that easy to try to guess what will happen, okay? If you have a computer, you can do it quite easily. You can put it in a model, and this is what you get. Here you have snapshots, you have people, and what you get basically is random movement. Okay, we are producing kind of random pattern. But this is not what we are doing at the individual level. Each of us is not doing a kind of random movement. We are following our A and B. Okay? So there is a complete discrepancy between what we are doing at the microscopic level and what we are producing as a macroscopic pattern. Okay? Now we can ask that people coming from outside, we can say, okay, we can give you some insight in the process if you want to. Because today we are able to trace people. Okay? For example, cellular phones, GPS. So here I take one people at random and I trace what he's doing, all these movements. So the question is, does it help you to understand the rules, what the person is doing? It is not that easy. Still, it looks like random movement. Anyway, maybe one person is not enough, okay? Because we are producing everything in the software here, so we can have the traces for everybody in the stuff. Like we are all dreaming big data, being able to follow people all the time, okay, to trace people. And this is the kind of stuff we have. How can we extract patterns from this kind of information so that we can go back to the processes, the microscopic processes? I could give it to you. Maybe I can give it to Joanna. She's working on that kind of stuff. Would you be able, analyzing the traces, to go back to the rules of the game? This is a challenge. Very difficult. Okay? Because you can have an infinity of rules producing that kind of traces. Okay, so this is just to illustrate some of the limitations of the data. If you just have the data and try to begin from the data, then you will find some limitations very, very easily. Of course, this is called a Lagrangian approach. Okay, you are following all the traces. You could say, okay, something maybe simpler. Okay, I can track all the people. Every time they are moving somewhere, I count the number of people coming here. This is more called Eulerian approach, and this is what you get. At the beginning, it seems that, okay, it's fine. Okay. And then at the end, what you get is thank you very much. What you get is random map. Okay, so both Eulerian and Lagrangian does not help you much in understanding what happens. Now, nasty question. We just change very slightly the rule. I have to make sure that I am between my A and B this time. Okay, very small modification of the rule. What will happen? Yes, something different, hopefully. Yes, this is what you are doing, okay? But this is kind of logical. Okay, you know the rule. You can predict what you're going to do. But my question is, what are we going to produce altogether? Because this is what we are supposed to do. We're working on societies, okay? Unless you are a psychologist and you are focusing on one individual, okay? We are working on dozens, thousands of individuals doing things all together, interacting. Even loosely. Here it is loose interactions, okay? People are not coordinating. No one is saying, okay, keep calm, everyone stops. Who is my A, who is my B? Let's try to coordinate. There is no coordination in the game, but still we are producing patterns. This is what you get, okay? At the beginning it is completely random, and then very quickly everyone will be here, at the same place. Okay? So you have very slight modification of the rule, and at the end, you produce a pattern that is completely different from the first one. Okay? And if, once more, you take someone coming from outside, not knowing the rule, and ask him, what are we doing? There is no way he can get the rules just by looking at us. Okay? So, of course, you can say a lot of things about that very silly, stupid example. If you think about it, you will find the trap in the example. But then you have two main kind of information you can get from it. first, okay, it is very difficult to guess the macroscopic level from the microscopic, okay, in presence of interactions. Here we have interactions, even if they are very, very loose interactions. No coordination, okay? We are just connected because someone is my A, is connected to me. I don't know him, I don't know I am the A of someone, I don't care. Okay, I am just following my own A and B, that's all. So here simulation helps a lot. Okay, you put the microscopic in the model and you simulate to see what happens at the macroscopic level. But then, even more difficult, if you just have the macroscopic level, and this is most of the time what we have, for example, as geographers, as planners, we see city as a macroscopic object, it is even more difficult to guess the microscopic level. Because here you have an infinity number of possibilities producing that macroscopic pattern, okay? And this is called an inverse problem. It is inverse modeling, and it is much more difficult. And we have to admit that most of the time we are not trained to do inverse modeling, especially in social sciences. Most of our problems belong to inverse problems, but we are trained into problems, okay? Okay, so that first example was an agent-based example, okay? When I told you to do things, A, B, move, okay, I was thinking about you as individual agents doing things, having information, applying rules, and that's it. And this is how I put it in the model, okay? It was an agent-based model, very simple. The idea is that having that kind of model, you can run social experimentation, which is very difficult if you don't have models, okay? Because most of things are completely forbidden. It's a pity, it's a shame. We're not supposed to do anything with humans as experimentation, and it is much more difficult to understand what happens if you cannot experiment, okay? Also, the idea of that kind of models is to improve our understanding of the processes. You put things as a model, you run simulation, and you try to get if you're able to generate something that looks like the processes. If you're able to do it, then it is a notative explanation of the processes, the underlying processes you're looking for, okay? Then you get try to get some comprehension. And the fact that you are defining a model forces you to define precisely what you have in mind, okay? You have to write it. You have to give it to the computer, okay? So there is no miracle here in the middle, unless you put everything as garbage in the computer and then you produce garbage out, which is something that exists in modeling, of course, garbage in, garbage out. And of course, the idea that that kind of model should allow you to run some predictions, but of course, predictions in probability. And this is exactly what we have as example just before with the idea of cellular automata. That kind of models allows you to draw predictions in probability. The point is not, I'm not supposed to say exactly what will happen for that very small parcel among thousands of parcels. Okay, it's a statistical prediction about that kind of objects that are evolving. So of course, one question we may have is, what is the link between cities and self-organizing systems? Because if you think about it very, very rapidly, then you have a kind of paradox. Because if cities are complex adaptive systems, it means that no one is leading the cities. Some people are paid to do it, but if it is a self-organizing system, why should we pay people to be leaders in cities? Okay? And it's not a bad question, especially in France. When you think of the number of people trying to organize the whole stuff, we don't know if we need them or not. Okay? We should try without them, like people in Belgium did for some months, having no governments, and still, Belgium is still here. Okay? So let's check for something very quickly. This is a very good example. I like it very much from colleague and friend Itzhak Ben-Enson and his team in Tel Aviv. What they did is try to check empirically this hypothesis. Okay, maybe some of you know it. What they tried to do is to monitor for several years, okay, for 20, 30 years, what the master plan of urbanism was saying about what everything was supposed to become in the city, okay, and what really happened. And what they discovered is that for So this is the red line that is interesting, the percentage of non-conforming developments, okay? And you can see that at the beginning of the period, 15% of the developments were non-conform to the master plan, were just not following what was supposed to be done. Then, 10 years later, 50%, half of the developments, okay, were not related to the master plan. And then 65%, 10 more years after. Okay, so this is a very good point, because the master plan is the idea of trying to centralize. It is a top-down process. People are trying to organize the city and the way the city is growing. And then you have the city as a self-organizing system growing merely by its own, like a biological entity. Okay, and what happens in that kind of stuff? So when I present that kind of output in France or in the north of Europe, most of the people say, well, come on, this is Israel. Israel is cows. Okay, no one can do anything in Israel. Well, I've been in Tel Aviv, and this is not cows. I do not agree with this. Okay. Itzhak Ben-Enson have been doing the same kind of analysis in Finland. And what he discovered that on average, it is the same kind of output. Okay, on average, 50% of the development in the city do not correspond to any planning process. Okay, of course, it is embedded into a planning process, but that was not predicted by what was defined at a given date. Okay, because of many local interactions. And of course, they raised that kind of theoretical conclusions for people doing planning. There are some doubts regarding the degree to which the original land use map effectively contributed to guiding the actual pattern of developments. Well, it is not a disaster because we have beautiful cities, okay? And I do believe that it is absolutely crucial that we keep that self-organizing process in the city, okay? Because societies are self-organized processes, self-organized entities, and we do need that kind of properties. But then the good question is, no one is leading then. Of course, you have people leading, okay? You have many people trying to lead it. But the question is not, how can we make sure that things will happen in one direction? I would say that merely the good question is, how can we try to guide the course of these systems while you cannot imagine, you cannot identify very simple processes. It is not like being in a plane, okay, in which you have a limited number of movements in a plane. The degree of freedom is quite small, okay, for security reasons. And then you have buttons, okay, and then you can play with the plane. You know what happens, okay? If I want to turn left, I know what I want to do. If I want to turn left in the city, I don't know what to do, okay? So, and this is a definition of complex systems. So, my definition here is very broad. As soon as you have a large number of entities interacting locally within and with their environment, these entities being human or not, okay, it works very fine with animals, even with plants, with companies, okay, industries, whatever you want, components in the software also. And then the idea is that even if you have non-coordinated behavior, you may obtain global structures that are very organized, okay? If you have interdependency between the behavior of the entities. If you have no interdependency, if what I'm doing does not alter what you're doing, then there is no interaction, okay? We have no complexity in it. But if my behavior has an impact of your behavior, even a small impact, then we are in that case, okay? And of course, if we introduce coordination in the process, then we may be able altogether to produce something that is highly structured. But the point is that you don't need to have coordination in the system to obtain highly structured systems. This is the point. Of course, Schelling segregation model is a very, very nice and very well-known example of that kind of output, in which you have individuals, okay, evaluating their local environment and deciding if they are happy or not with the proportion of their neighborhood having the same color than themselves. If they are not happy with this, then they decide to move. So this is exactly the idea of the party game. Every agent is just embedded in the very local environment and takes decision based on that. He has no idea of what is producing at the global level, and he doesn't care, okay? Very loose interactions between all individuals. And what you get, of course, this is very well known, is that kind of output in which here you have the density of agents. So 30% means you have 30% of space occupied by agents, okay? Very small density. So 98% is very dense. And what you get here, from the bottom to the top, is the tolerance, okay? So when you have lambda equals 80%, it means that the agents are happy even if they have 80% of the neighborhood having a different color from themselves, okay? So if I'm, let's say, black, because that was the idea of Schelling model, I'm black, and around me 80% of my neighbors are white, I don't care, okay? If I'm here. If I'm here, I need to have at least 20% of my neighbors being different from me. So I need to have 80% like me. Otherwise, I'm not happy. Okay? So this is a scale of tolerance. And what you get is that if the density is small, nothing happens. You're in the middle of Australia, you don't care if your next neighbor who is 500 kilometers from you is green, okay? Even if he has 4 legs, you don't care, you never see him. But when the density is increasing, then you increase the loose interactions between the people. And then strange things happen, okay? And what you get is that kind of output, okay? That here, even if individuals are very, very tolerant here, they are ready to have 70% of people having a different color from them in the neighborhood. What you get as a macroscopic output, this. In the cities that is not integrated at all, okay? On average, you have a very small proportion of contacts between neighbors having different colors. So you have a discrepancy between what happens at the microscopic level and the macroscopic level. It is always the same story. And of course, when you reduce the tolerance, you increase segregation. But this is quite trivial, okay? And then at the end, this is what happens when people are just moving all the time because they are looking for a place where there is no strangers, okay? What is important with that kind of dynamics, it doesn't tell you anything about segregation, okay? And Schelling himself was still alive, and he cannot believe that people are still working on this model because he's been doing this model very rapidly one day, okay? So this model doesn't tell you anything about segregation because it is so simple that it can hardly be applied to real situation. What it tells you that you should be aware that every time you try to make a connection between individual behaviors and macroscopic patterns or behaviors, you should be very careful. Anytime you have interaction between the components. And in a social systems, we have to assume that we have interactions everywhere. Loose interaction and very tight interactions. But then that kind of pattern is very bad because it means that if you do not regulate the system, then the system is going in a direction that maybe you don't like. Okay? We are producing segregation while we don't even know it. We don't know what we are doing. We are just moving, okay, taking local decisions, and we are producing something that nobody wants. So the question is, how can you make sure that we modify the course of the system, okay? So we have to improve regulation. And it is very difficult to try to fight again that kind of Schelling dynamic. Very difficult. While it is very, very easy to amplify the dynamic. For example, here, if I replace the original regular network of Schelling with networks that are highly clustered, in which the neighborhoods are very, very dense locally and have very small connections with other neighborhoods, and this is what happens here, okay? Then what you get is an amplification of the process. What you create are cliques and traps, places in which people, when they are trapped, they don't have to move anymore. They are protected against the other color. And this is what you can see from that picture. So here you have the tolerance on that axis, okay? So 100% it means that people are happy all the time, they don't care, okay? And 0%, they're happy only if there is no stranger in the neighborhood. So here what you get is that the blue and green colors are for the grid and random network. So here you have a kind of typical result from Schelling model in which here the mixity index decreases rapidly around 70%, okay? So this is the output I showed you firstly on the maps. But then when you see that if you use scale-free or simplistic network in which you have highly clustering network, then here you are able to find solutions even if people are looking for a 0% neighborhood, while it is impossible for a regular network. So very easily you can amplify the dynamic of the model, while doing the opposite, very difficult. Many people try to do it, we still don't know how to do it, unless you put things like, okay, my agents do know what they are producing and they do not agree to produce segregation, so before moving they are evaluating the global stuff, and if their individual behavior will increase the global segregation, then they won't move. Come on. This is very difficult to put in a society. This is exactly the problem of sustainable development, to try to put more macroscopic stuff into the microscopic brain of the agents. This is one way of doing it. It is very difficult to do it, okay? Of course, as societies, human societies, we should be able to do it, but it is not that easy. Anyway, that kind of model is a very good example of the discrepancy between individual utility and collective utility, okay? So here, the rats, they were all trying to maximize their individual utility by getting the piece of cheese first, and what they did is that they maximized the utility of the human who put the trap, okay? And then they minimized the utility of the rat group. So this is something that is well known in economy, okay, even in mathematics, the fact that it is very difficult to have at the same time maximization of individual and collective utility. And of course, Schelling model is completely oriented toward maximizing individual utility. This is the idea. So one thing we can do to try to improve that kind of regulation is to try to introduce cooperation, with the idea that by cooperating, maybe people can try to extract their very selfish behavior to something that is more global. Okay? So move from Nash equilibrium maybe to Pareto equilibrium. And agent-based modeling allows you to do things quite simply. You can define games with agent-based models in which you add people into the game. For example, let's imagine a city, very simple city, theoretical city, in which you have workplaces, universal places, okay, commercial services, and home places. And then you put agents in the model, very simply. For example, you choose their home randomly, okay? Then you choose for each agent workplace, which may be also completely randomly. And then you fix a trip chain. You say, okay, every agent will have to move every morning, leave home, then go to work, go to the universal services, post office, for example, then commercial service, then go back home. Every agent. So if you have 100 agents in the system, everyone will have to do it. And then you define your utility function, your objective function here, that each agent will try to minimize the total trip chain. Okay? Just to make sure that you don't have just a random system. Okay? So of course you have a stochastic system because you have some random component in it. Okay? But then each agent has a very, very specific utility function, the same for everyone. This is completely rational. Just find my different places to make sure that I minimize the total distance I'm covering. And then when you put in a system, it's traffic. Because if you have no traffic, it means you have no interactions. You just have ghosts doing things and nothing happens. But if you make sure that every time you have one more person on the road, then you increase the traffic and then you reduce the speed of the other people, then you create interactions. The more people you have on the street, the less speed you will have. Okay? So every agent in the system will modify the environment for the other agents. Okay? This is the kind of output you have as a game. Many parameters, okay? And many outputs, because the idea is to make sure that each player can define what is supposed to be for him the best city as a sustainable city, knowing all the rules and trying to minimize some negative externalities. For example, the production of pollution, the production of traffic. To make sure to position the services so that people are using services. Having workplaces in which people are working, okay? Having public services in which people are going, but also make sure that everyone can have access to a public service. You can put some buses lines to try to reduce the car sharing. Okay, you can do whatever you want in the system. The idea is you have to define yourself what would be for you a sustainable city, because everyone is talking about sustainable cities. And when you put people working on it as academics or people from companies or people from cities, you put them in front of the model, suddenly they don't know what to do, because they don't have a very clear definition of what would be a sustainable city. Very rapidly they say, okay, for me, a sustainable city would be a city in which everything would work fine. Okay, how do you define it? I want to make sure that, okay, all my services are used by the people, so no one is losing money. But then I want to make sure that people are not crowded in the same places in the traffic, so I try to arrange my services. But then I cannot control everything, because every agent is doing his trip chain. I don't know exactly what the people will do. And the trip chain, even if it is simple, it is long enough to be unpredictable by your human brain. You don't know exactly what will happen if you just change one service from one place to the other. You have to run the simulation to see what will happen. Okay? So you have to play with the model. It's a kind of system in which you have an intuition of what will happen, but you can train, okay? You can learn from it, but still there is part of it that you don't get really, okay? Then you learn from the system, okay, you're very happy, you're able to produce something that, okay, you're quite comfortable with. Then you discover that just to obtain one output, what you did is that you just hid or maybe just forgot many things. For example, you put buses everywhere, okay? And we have this fairly well-known example here. You put people from bus companies. Every day they are trying to minimize the cost of the company, so not putting buses lines everywhere. Here in the model, after 10 minutes, they just put buses everywhere. Even buses were driving at 50 kilometers per hour, okay? Just because they want to improve the sustainability of the city. And they just forget all the constraints, okay? And then people are very happy. And you tell them, okay, now you know how the system works, so now let's move to another platform, exactly the same model, but this time you're going to share your city with other gamers. And this time you won't be God in the model. You will have only one limited power in the system. For example, you will be the one working on the economic side. So you will have the capacity to modify the location of the services. That's all. And of course, you will get information from the model on the number of customers you have for your services. Then you will have one public agent working on the road network, public transportation, air pollution, that kind of stuff. Okay? And then you will have citizens. You will have one player that will be responsible of citizens. If citizens are not happy, then he will be able to change the location of their homes. So everyone here has now a very specific role into the game, okay, and has very specific objectives. And of course, the idea that your objectives are different and depend on your role, okay? Because if everyone had the same objective, then you converge, because you introduce coordination. But if everyone has different objectives, And especially if everyone doesn't know what are the objectives of the other gamers, then you don't know what happens. You have to play. And of course, you don't tell the gamers anything about cooperating or not. Okay? And you can imagine that here, in that kind of system, there is nothing to win. You're not supposed to be the first one. There is no such definition in the system. You can imagine that the people would try to cooperate very, very quickly. And this is not what happened. You just look at them, okay, and see what happens. See, for example, if they are able to produce altogether kinds of cities that have given properties we may know, given some kind of objective functions. This is the prototype, so people can play here in the same room or at distance, okay? And what you get from that kind of game is that people do not cooperate. This is not natural, okay? Because first, they want to understand what happens. And they are very upset to discover that they don't understand what happens. Because every time they try to do something, then the other gamers are doing something else. And they didn't take into account what they are doing. Well, okay, obviously, because they don't know what they want to do. But before going see the others and try to say, okay, what do you want to do? This is what I try to do. It takes a long time, okay, even for people from the field. The fact also that gamers tend to focus on the local objectives more than global ones. Okay? Every time they lose that they are all trying to produce a sustainable city. Okay? They are attracted by their objective function. I want to make sure that my services have customers. This is what I have in mind. And I completely lose the global objective. The temporal projection is also very limited. Okay? Only a few of them are able to have a very long projection to see, okay, if we need a sustainable city, then we should have all these different steps. Okay, very difficult to reach that kind of stuff. Of course, even if the model is simple, then you still have these strip chains that make sure that you don't get a full understanding of what happens. Okay, and your capacity of predicting the output is limited, so you need the model. You need to run the model. Every time you have that platform, okay, and this is what happens with the city, okay. We don't know exactly what happens with the city. We have vague ideas, we have intuitions. We try to do things and see if what we get as outputs is coherent with our expectations. Okay, and of course, what we get also as an output that most of the people get disappointed and they prefer the position in which they can decide about everything. And they don't like very much the situation in which they have to compose with other gamers. Even if they realize after the game that this is exactly what they're doing every day. Every day they are supposed to compose with many different peoples from many different fields, just working on the same object. Especially for people working at the city level. Okay? There is no God in the city. You just have people having limited understanding of, limited view of the object and trying to compose with the others. Okay, so very quickly, would that kind of conclusion would be, okay, so agents can make a difference. We should move to agents. Of course, agents are very nice because the formalism of agent-based modeling is much closer to the understanding of much people in social sciences, okay? Because you don't have the front wall of mathematics. Even if you have mathematics behind, you can define quite easily an agent-based model. And of course, it is a very good thing because you can give the capacity of defining their models to social scientists. They can define the models they need by themselves, okay? And this is something that is very good. But, of course, if this is just what you're doing, then you may have some drawback. It means the model you are producing this way, if you're just doing things this way, and because you're able to do it now, then I don't want to interact anymore with people from mathematics, with computer science. We've been doing for many years. It's a loss of time, loss of energy. Okay, now I'm free. I can move to my own models. Well, very easily you will be disappointed because we need to put energy into cooperation with other disciplines more than ever, even with that kind of very simple model and the capacities we have today to develop our models in our fields. So I would like to finish with model coupling. I do believe that in the future, all the relevant models will be coupled models, which means models that are able to take the diversity of the formalisms that exist and put them all together to answer questions about real life, because real life is based on coupling of processes at different scales, different times, different levels, different speed, and you cannot put everything in the same logic, even if we try to do it in modeling, because it is easier for us to do it. So I will just finish with a very simple example of an epidemic spread. Okay, if you try to model the spread of an epidemic at the worldwide level, you can use agents. Some models are doing it. You can have millions of agents in a model. It runs. Does it make sense to have millions of agents in which you have everything? You know where the agent is moving, is living. So this is my cell phone telling me that I should stop. So we can do it. Technically, we can do it. Okay? You can imagine where the agent is living, where it's moving, taking which plane, having the disease or not, and then spreading the disease. And then when you arrive in Abidjan, for example, then it will take the train, then move, then take the car. You can put everything in the model. Okay? At the end, what you get is a lot of noise in the model, because you have so many parameters in the model that you don't really get. So you can force the model to fit with the data. You can do it. You can adjust. But in terms of understanding of the processes, then it's difficult. So there is also a discrepancy between the capacity of prediction of a model and its capacity to get some understanding. Okay? These are two different objective functions. Prediction is not explanation. These are two different things. So of course we know the properties of the macroscopic and the microscopic kind of modeling, for example, dynamic system based on differential equations, that are very well known in epidemiologic modeling, and you can try to put them in the same model. Of course, you can say everything with the dynamic system at the macroscopic level. If you put very strong hypothesis on the disease, then you can restrict completely the modeling of your disease to a set of differential equations, and then you can have very nice output from the model. Okay, and it is very, very good because you can analyze everything from a simulation, even by introducing the flows. And this is called a metapopulation model, in which you have, for the most simple example, SIR, susceptible people, so people like you now being able to catch a disease, infected people, for example me, I get something in France and I'm just gently bringing it to you, and then you will have people being recovered at the end of the epidemic. Okay, if you make assumptions by the fact that we are all mixing randomly, okay, then you can use the SIR at the macroscopic level using differential equations that will give you the proportion of people that will move from S to I, from I to R. Very nice. And you can put it as flows also. This is what you have here. But then what happens if you put things a bit more complex? For example, you have one agent that decides to take the plane, and finally it doesn't take that one, but change directions because he knows that where he was supposed to go there is an epidemic, and then he decides to cancel his flight and take another one, that kind of stuff. Very difficult to put it in a kind of macroscopic model. So here you can couple the models. For example, you can say, okay, so each city is a node in the system. So as a city level, I have maybe 1 million inhabitants, okay, 10 million inhabitants. It doesn't make sense to have 10 million agents. I don't know what they are doing. Okay, they are just moving randomly. At that scale, it's kind of completely random movement. So here, you can have one set of differential equations for each city. And then you say, okay, but then when the people are taking the flight and during the flight, it is not random movement. You have interactions, you have individual behavior. So here, what happens during the flight, you have agents. So you have a set of differential systems that are all connected for the city. You can have thousands of them, and then you have thousands of flights, and for each flight, you have agents within the flight. And then you have the spread of the disease, very different processes, but that should work at the same scale, temporal scale. It is not that easy to do it, but we can do it, okay? Of course, what you should do here, you have two kinds of models, the completely macroscopic one, the complete microscopic one, the coupled one. You should make sure that under certain assumptions, they produce exactly the same output. And for example, this is what we do every time we try to compare our model to the so-called mean field approach, in which we take very strong assumption. What happens if you have instantaneous trips, complete network, constant mobility rate, and that kind of stuff. And then you make sure that all your models produce exactly the same output and are able to produce exactly here the same maximum number of infected people at the same time and the same duration of epidemics. And then you release the assumptions. So they are all have the same background, and then you see what happens if you release the assumptions. Okay, hoping that the coupled model is able to do much better than the macroscopic one or the microscopic one. And then when you discover by doing it is that if you put strategies in your model, then you obtain very different behavior. For example, here I will just finish on that one. If you put quarantine in the model, okay, it's a containment strategy that says, okay, if a city reaches a given level of infected people, then no one is moving to the city and no one is leaving the city. This is quarantine. And then when you get, so this is a maximum number of people being infected. In the red dots are the output for from the macroscopic model, metapopulation model, which is fairly used in that kind of modeling. And here you have the coupled model. And what you get is that the dynamic here for the maximum interaction, number of interaction based on the threshold. So here the threshold is the proportion, the threshold value to get before putting quarantine. Okay, if you put the threshold at 0, every time you have one more than people infected, you get the city. No one is moving from the city. Okay, very bad. And of course, then you kill the epidemic. In that, if you have a macroscopic model, you lose all the details about the epidemic. You don't know what happens, okay? And every time you open the door of your cities, because it is a continuous model, you will have people, you will have spread of the epidemic. Whatever happens, you won't be able to do it. While if you have a coupled macro-micro, in which you have people being individuals, being put in flights, and having individual discrete probabilities of giving the disease, then you introduce variability in the model, which are much more interesting. So my conclusion would be that, of course, agents are very promising. Well, they've been promising in the last maybe 20 years, but among other approaches. The idea is not to replace everything by agents just because it is easier, okay? It is a very false idea, because once you have your agent-based model, then it will take you ages to analyze the behavior of your model. You will need to run intensive computation to understand what happens, okay? It will be much more difficult than doing the differential equations, okay? This will be painful, but once you have it, you can understand the behavior of your model quite easily because you have all the tools. Doing agent-based modeling, the opposite. Very simply, very rapidly, you can define a model, a crappy model with thousands of parameters, and then it will take you a century to understand what your model is doing. There is a price to pay for any agent-based model. So unless you don't care about that, you just care about doing a model that is flashing, okay? If you just want to produce real knowledge and scientific stuff, then there is a price to pay. So the idea is to put agents whenever you need them and not putting them if something better can be done. But then it means that you need to work with people from other disciplines. So my conclusion will be the one from Albert Simon, Nobel Prize in Economy and Turing Prize in Computer Science. There is no one best way to do things. Okay, this is what I do believe. Thank you very much.
Okay, thank you for this interesting and enlightening presentation. Estamos bocadinho fora do prazo, mas acho que ainda temos tempo para fazer umas perguntas. Não sei se alguém dá assistência.
Não queria saltar thank you very much for this very enlightening vision about agents. And I would like to hear your thoughts about intelligence. I mean, you spoke a little bit about this, but typically I think the agents are very dumb in the sense that they follow simple rules, and we see an intelligence emerging on a global level. But my question is, what if the agents are intelligent themselves? You know, how would you see, for instance, the possibility that you know, through genetic algorithm, each agent could adapt themselves and in a certain way and optimize his behavior, and this would be a little bit like combining artificial life with artificial intelligence. I mean, how do you see this kind of approach? Thank you.
It's a very nasty question. I think it depends merely on the goal of your model. If your goal is improving your prediction capacities, I do believe that doing this is a very good idea. If your goal is trying to understand what happens, then it's a very difficult way of doing it. I try to do it for mobility purposes. We've been defining a mobility model at a city level, having thousands of agents, being able to adapt themselves, to learn from their experience and to adapt their behavior. For example, I'm leaving the morning to do my trip chain. I discover that it took me 1 hour and a half to do it, while I was supposed to do, just by looking at the internet, that in 45 minutes it would be fine because of the traffic. So I decide the next morning to learn from it and to modify my behavior to find a better way to do it. And every agent is doing it. Once you get at the end, that the agents are just evolving and you don't understand anymore what happens. Okay? Unless you constrain very, very tightly the domain of variability. But then it doesn't make sense to let them evolve. So it is very interesting to do it in order to let the agents find solutions that you wouldn't be able to find. And this is very nice to do it. So for optimization, for example, it is great. But if your objective is to understand how the city is behaving, because of course we are all intelligent agents, we are all learning, we are all adapting, and we have memory. Okay, these are three main components of intelligence. And of course we are able to coordinate. Then if you want to put everything in the model, you won't understand anymore what will happen. So this is my feeling at the moment. But I do believe that for prediction it is very important to have systems that are able to learn in order to optimize themselves.
So do you think basically it will be more efficient, but the box will become even blacker? No? So
yeah,
okay.
Exactly.
Thank you.
Exactly.
Mais alguém? Ih, não acredito. Deve estar tudo com fome, mas como as apresentações estão interessantes, ninguém tem mais perguntas.
Bom dia, eu queria perguntar ao professor Tenório a área de estudo se foi só por timão, se a área de estudo foi só essa, e quanto tempo demorou a fazer o levantamento, ou seja, a conseguir todos os dados para poder fazer essa análise espacial.
Mais questões?
Dório, porque eu complemento a pergunta da Ana, porque efetivamente um dos grandes desafios, como tu disseste, era a questão da administração, estar a desinvestir na informação, não é? E ainda por cima na georreferenciação, em toda este manancial, este potencial, não é? De dados e de sistemas que nós sabemos que pode ser utilizado. E, portanto, a pergunta da Ana, eu penso que é a preocupação, que a Ana é técnica, não se identificou, mas é exatamente depois que temos que arranjar aqui uma situação de compromisso, não é? Entre o que é a situação ideal e aquela que pode ser a potenciadora da melhor utilização. Portanto, era também para te ouvir sobre isso.
Relativamente, obrigado pelas questões e Relativamente à primeira pergunta, portanto, para Portimão, há uma justificação prévia, porque é uma série tão longa de dados, não é? Portanto, 1947 a 2010. Precisamente porque era uma das vias possíveis para detectar as estruturas profundas, entre aspas, não é? Portanto, a tendência que, apesar da mudança, permanece. E, portanto, por outro lado, criava robustez também no modelo, nomeadamente nas probabilidades provenientes das cadeias de Markov, não é? Portanto, é quase uma exigência matemática que tenhamos séries temporais longas. Agora, a sua pergunta é, a área de estudo, sim. A área de estudo foi só Portimão. Na realidade, o critério administrativo não serviu como critério para determinação da área de estudo. Mas acabou por ser, porque a área de estudo foi obtida por aquilo que na Universidade da Catalunha se desenvolveu, que é o modelo de potencial com base nos movimentos migratórios por efeitos de trabalho de escola, que está publicado em várias revistas, nomeadamente na ACE, indexada Scopus. O que acontece é que nós íamos apanhar 2 freguesias, ou suponho 2 ou 3 freguesias do concelho fronteiro a Portimão, do lado leste. Acontecia que, em termos de dados, estávamos não era a duplicar, mas a complexificar muito o trabalho, não é? Porque tínhamos que ir contactar com 2 câmaras, consultar processos numas, consultar processos de 8, e, portanto, isso complicava o processo de aquisição de informação. Portanto, apesar de ser bonito dizer que a nossa área de estudo não utilizou um critério administrativo para a seleção, isso é verdade, de facto não, o critério não foi esse, foi o critério que acabei de dizer, portanto, o modelo de interação. Mas, na prática, acabou por ser só o concelho ficaram de fora 2 freguesias e, portanto, este modelo resolve não, é aplicado para Portimão e não para aquelas 2 freguesias que ficaram fora por esse. Quanto tempo? O trabalho depende do trabalho que estivemos a fazer, portanto, ou seja, se é o tempo de aquisição de informação e o tempo de modelação. Atenção que esteve a trabalhar aqui...
No fundo é o tempo que a pessoa que fez a tese decidiu que ia fazer sobre aquela área, falar com os interlocutores e ser-lhe disponibilizada essa informação.
Sim,
informação muito complicada de
sim,
conseguir. Sim. Era isso que eu estava a tentar perceber.
Sim,
e se a pessoa em si tinha relações estreitas com esse município, ou se era só por... porque é mais fácil de obter essa informação ou não. Infelizmente é assim que funciona.
Sim, claro, evidente. Eu, relativamente a essa pergunta, o que eu lhe posso dizer é que o agente estudante de doutoramento tinha uma proximidade muito grande ao agente serviço técnico. Não lhe posso dizer mais que isto. Mas o que não quer dizer que, lá está, se nós temos um património quase que diria, de histórico sobre o crescimento das cidades, e nomeadamente sobre os subúrbios urbanos injustos, brutal. E temos esse património que não é transparente. Alguns têm, os outros não têm. E só os têm quando se está mais próximo. Portanto, a estratégia que eu aconselho a todos os meus estudantes de doutoramento assumindo essa responsabilidade é aproximem-se. Porque, na realidade, é difícil trabalhar com esta dinâmica de agentes. E de modo que eu acho que esse património é pena que não esteja, digamos assim, catalogado e acessível a todos, não é? Portanto, quanto ao tempo, o tempo de aquisição de informação deve ter sido para análise visual de imagem e tratamento em sistema de informação aproximadamente 1 ano, mas 1 ano. Relativamente à construção do modelo, à calibração do modelo, sobretudo 3 anos. Mas trata-se de um trabalho de investigação. Não se trata, quer dizer, na realidade, ou era bom era que os municípios, a administração agora pegasse neste resultado e experimentasse internalizar no processo de trabalho da administração. Isto é que seria interessante, porque agora corre depressa. Eu já agora passo a publicidade, parece quase um vendedor de teses, mas, de toda a maneira, cumpre-me fazer isto também, é a minha obrigação moral, não é? Quer dizer, a Raquel de Deus tem pedido por mim, aliás, não foi pedido, foi um bocado pedido, um anexo técnico brutal, quase que diria que é um guião para replicar o modelo. Não é? Portanto, nomeadamente software, que não vai na tese, não é? Quer dizer, há uma parte que não está na tese, mas é uma espécie de manual prático de utilização do modelo numa escala local, não é? Mas falta fazer o resto, evidentemente. Relativamente à questão do desenvolvimento da informação geográfica da administração pública, sim, claro, sim, exatamente. Eu creio que sim, que respondi em parte. Eu acho que não vamos... Eu, pelo menos, não estou nada interessado em entrar em polémicas sobre o desenvolvimento da informação geográfica da administração pública, mas acho que... Eu quando disse isso, referia-me especialmente aos municípios. Acho que os departamentos que estão a ganhar mais não são seguramente aqueles que têm o serviço de SIG incorporado. Não é? Portanto, não são os departamentos de urbanismo e planeamento que estão a ganhar mais, ou nas grandes opções do plano, no final do ano, não é? Nem que se traduzem depois em financiamento, como é evidente. Não é? Mas é uma impressão, como eu tive o cuidado de dizer. Não sei se isto é certo. No que diz respeito à infraestrutura de dados nacional, há coisas que vão ficando para trás, não é? Ou adiadas, etc. E, portanto, é um bocado de pena. Não sei se respondi.
Thank you very much for the presentation, Arnaud. It was very interesting, your talk about agent-based models. And there are some issues concerning calibration and the validation of the model. So how do you know when you have too many agents? Your example that you can have 1 million agents, but then you're overfitting the model, or you're getting too much noise in the model. So how do you know when you have too much agents? How do you know when your model is overfitted? And how can you validate the model? Also linking with Professor Tenodorio's presentation, how can we transfer the knowledge that we get from the processes of the model to the decision-making agents or entities?
Okay, so 2 nasty questions in one. Thank you very much. And I have 2 minutes, right? Okay, so the big deal is not the number of agents, because if you have the computation power to do it, you can put agents. The difficulty is the number of parameters, because each agent is defined by a certain degree of freedom, okay, and then you multiply the combination of parameters when you increase the number of agents. And it doesn't make sense to have thousands of agents, millions of agents, if they are very simple, all the same, exactly. So the main question is the number of parameters, and we have very nice protocols now to try to assess how the variance increases with the number of parameters, and this is a very good idea of the idea of overfitting and over-parameterizing a model. So you have to look at the variance of your outputs. You have a whole kind of work on sensitivity analysis that is very well defined today, and that you should run anytime you have an agent-based model, and it is a very long process, because the idea is to try to analyze the combination of parameters and look at their impact on the behavior of the model to identify the variability and the robustness of your model in front of the variability of the parameters, and then to try to assess the importance of each parameter compared to the others, and then all the possible combinations. So honestly, it's a pain in the ass to do it. Every time you have more than 3 parameters, it's a very long process. The good point is that we are evolving. Now we have tools to do it. For example, when you were at the Complex System Institute in Paris, we were developing the OpenMol platform that is now very advanced, one of the most advanced in the world, that is still free. And you can use the OpenMol protocol to spread your model on a grid of computers, using all the algorithms that are available here to analyze the sensitivity of your model, but also to try to calibrate your model in a more or less automated way. Because one way of solving the problem is to say, okay, as soon as I have more than, let's say, 5 parameters, it's impossible to check and explore all the combinations that are possible. So I can also try to reduce my space combinations by trying to calibrate, by defining objective functions. For example, I want that my model is able to reproduce that kind of phenomenon. Let's try to find the possible combination of parameters that are able to do it. So, and this is an inverse problem. And you have a whole set of algorithms based on genetic algorithm in the open world software that allows you to do that kind of things. So it depends very much on what you want to do. But I would say that now, with the technologies and the knowledge we have, developing a true agent-based model that is useful, not just a toy model with 2-3 parameters, I would say that 20% of the time you spend is developing the model, and 80% is trying to understand what the model is doing, calibrating it, and that kind of stuff. And if you don't have the right tools and the right platforms to do it, there is no way that you can increase your behavior, your knowledge on the model.
Mais uma última pergunta? Não?
Last question. It was about the transfer of knowledge. And how can we use this to the municipalities and master plans to apply it?
Okay, yeah, that was the second part of your question. Thank you very much, Patricia. In my mind, yes, corresponding to my different collaborations with people from cities, from professional companies, industries, one of the main outputs is to let them discover, just by constructing the model with us and then playing with the model and looking at the outputs, suddenly discovering that the whole set of parameters that they did believe at the beginning that were absolutely fundamental, like everything is absolutely crucial, you need to put this and this and this in the model because everything is important, you discover by doing the model, running the sensitivity analysis, that that's false. Not everything is important. You have most of the time a limited number of parameters that are absolutely fundamental, and the others are just noise in the system. And then by doing this, you introduce a gaining of understanding in the process. But then to do it, it is very constraining, because you have to make sure that the agents you are working with are developing the model with you. If you just meet the agents, okay, people from cities or from companies, you take their problem, you define the model, and you give them output, they won't believe you. And they won't have any ideas of what you're talking about. While if you take time to develop the models with them, which take years to do it, it's a very painful process, but also very nice. If you do it, really, then at the end, everybody is learning from the process. Because doing a model is learning. Because for just to define a model, when you have many people around the table doing a common model, you have to learn a lot of things to do it. Just by doing this, you are learning about the object we are all working on. And then you can give them outputs. And they are ready first to have an intuition of what the outputs are telling them, and also they are ready to accept partly these kind of outputs. So for me it's a very long process, and it is a very false idea that today we are able to define very, very quickly models because we have tools to do it, because we have the technologies, because we have the concept, we have everything, and then people on the other side will be ready to be fed with that kind of very quickly done model. This is absolutely false.
Então, resta-me agradecer ao professor Arnaud e ao professor Tendório pela sua presença, também a todos os presentes. Pediram-me só para informar que, como nos atrasámos um bocadinho, a sessão da tarde, em vez de ter início às 13h45, terá início às 14h15. Portanto, começamos um bocadinho mais tarde, para todos terem tempo de almoçar descansadamente. Obrigado.